All right, in this video, we're going to talk about section 3.7, dealing with the chain rule. And in this section, we'll be calculating derivatives using both versions of the chain rule. Now, many of the differentiation rules that we already talked about in previous sections can be inadequate for finding derivatives of most composite functions. Okay, so in this section, when we're using a chain rule, we're going to be taking the derivative of composite functions. Let's say we got f of x is equal to x cubed and g of x is equal to 5x plus 4. Then the composition of f with g, or f of g of x, would be this. We substitute the x in the f of x function with g of x to get 5x plus 4 quantity cubed. Now, this function can be first expanded and then differentiate, and then we can differentiate the polynomial. All right, because we can write that using, because we're cubing a binomial, we can expand this out and then take its derivative of that expanded function. However, if you have functions like this, 5x plus 4 raised to the 100th, then expanding this out would be very time consuming. So that means we're going to need a better approach. And this is where the chain rule comes in. So here's Theorem 312, called the chain rule. Suppose y is equal to f of u and is differentiable at u equal g of x, and u is equal to g of x is differentiable at x. The composite function, which is y is equal to f of g of x, is differentiable at x, and its derivative can be expressed in two different ways. So the first version would be like this. dy dx would be equal to dy du times du dx. Now the second version is going to be something like this. Let's say we have the derivative with respect to x of the composition of f with g of x, or f of g of x. Here we take the derivative of the outside function, which is f prime of g of x, and then it's going to be multiplied by the derivative of your inside function, which will be g prime of x. So these are the two versions of the chain rule, and we're going to look at each one of these versions to take derivatives. So if I use the first version, version number 1, here's the procedure for that. Here we're going to assume the differentiable function y equal f of g of x is given. Number 1, we want to identify an outer function of f and an inner function of g, and let u equal to the inner function g of x. Then number 2, you're going to replace g of x with u to express y in terms of u, and then y is equal to f of g of x. Here, if we let u be g of x, then that's going to mean that y will be equal to f of u. Now here we calculate the product dy du times du dx. Okay, since y is equal to f of u, we take the derivative of y with respect to u, and u is equal to g of x. That means du dx will be the derivative of that g of x function in terms of u with respect to x. And then finally, we'll replace the u with g of x in dy dx to obtain, dy du to obtain dy dx. So in this case, let's look at some examples of just that. All right, so in this first example, we're going to use the chain rule to calculate dy dx. And here we got y is equal to 5x plus 9, and that quantity is to the 8th power. And in this case, we're going to use, I'm going to use both versions in this problem to show you that you're going to get the same answer for the derivative of y with respect to x. Right, so if I use version 1, this is what I will do. I will let u equal to the function on the inside. In this case here, that 5x plus 9 that you see here, that would be u. So I'm letting u equal to 5x plus 9. And if u is equal to 5x plus 9, then this means that my y would be equal to u raised to the 8th power. So u is equal to 5x plus 9, and y will be equal to u to the 8th. Now let's calculate du dx. Okay, because u is in terms of x, so du dx would be equal to the derivative of 5x plus 9 would be 5. So du dx will be equal to 5. And then for the y equal u to the 8th, the derivative of y in terms of u is going to be this. We bring down the 8 in front of the u, copy the u over, and it's going to be to the 1 less power. 8 minus 1 would be 7. So dy du is equal to 8u to the 7th power. Okay. And now we can use those two to find out what dy dx is. That's going to be dy du times du dx. Well, dy dx is that 8u plus 7. dy du is 8u to the 7th times du dx. Well, du dx is just 5. So I have 8u to the 7th times 5, which gives me 40u to the 7th. Now I got to do the back substitution because I started that problem off as an equation of y in terms of x, then dy dx has to be an expression in terms of x. So I replace the u with the 5x plus 9. So I have 40 times the quantity 5x plus 9 raised to the 7th. Okay. So that's version 1 of the chain rule. Okay, now let's look at version 2 of that chain rule as well. So here's version 2. Our equation was y is equal to 5x plus 9 raised to the 8th. Now the way we use version 2 would be this. Here we bring down the exponent of 8 in front of the parentheses. So we bring down the 8, copy over the expression 5x plus 9. And then that 8 will be reduced by 1. It's going to be to the 1 less power. So 8 minus 1 will be 7. But then we got to take the derivative on the inside. The derivative of 5x plus 9 would simply be 5. Now, if I multiply 8 times 5, I would get 40. So it'd be 40 times 5x plus 9, and that quantity is to the 7th power. And if you notice, we get the same answer using version 2 of the chain rule. Okay. All right, take a look at example 2. Let's say we have this. Now here I'm going to use version 1 of the chain rule to calculate dy dx. And in this case here, y is equal to cosine cubed of x. Okay. Now, I'm going to write cosine cubed of x in another way as y equal to cosine of x, and that's going to be cubed. Okay. Now I'm going to use version 1 of the chain rule by letting the u equal to cosine of x. So here I'm going to let u equal to the cosine of x. And that would mean that y is equal to u raised to the third. Now I'm going to find du dx. So that means that the derivative of the cosine of x, if you remember back in section 3-5 when we were talking about the derivative of trigonometric functions, the derivative of the cosine of x will be negative sine of x. And then dy du, for u to the third, we bring the power down, copy over the u to the 1 less power. So it'll be 3u squared. And now we can find out what dy dx is going to be. So dy dx will be dy du times du dx. Or dy du, we found that out to be 3u squared, times du dx is negative sine of x. And now we can replace that u with the cosine of x. So it would be 3, well, I'm going to put the negative in front. So it'll be negative 3 times the cosine of x, and that's squared, times the sine of x. And I can write cosine of x and it's squared. I can write that as the cosine square of x. So it'll be negative 3 times the cosine square of x times sine of x. And that will be the final answer for that problem. So using the first version of the chain rule, dy dx, or the derivative of the cosine cube of x will be negative 3 cosine square of x times the sine of x. Okay, example 3. Use the chain rule to calculate dy dx. In this case, we've got y equal tangent of 3x to the 4th. Okay, now what I'm going to do here is, and it didn't say which version to use, but if I use the first version, version 1, I would do this. This will be the u, that 3u to the 4th. So I'm going to let I'm going to let u equal to 3x to the 4th. Let u equal 3x to the 4th. And then y will be equal to the tangent of u. Okay, u is equal to 3x to the 4th, and y is equal to the tangent of u. Now, let's find out what du dx is and what dy du is going to be. Du dx is this. Bring this 4 down, multiply it by 3 is going to be 12. Copy over the x to the 1 less power. So it'll be 12x cubed. Now for the y cotangent of u, we can find dy du. The derivative of the tangent of anything is going to be the secant square of u. That's one of those 6 derivatives of trigonometric functions back in section 3.5. Make sure that you know those or familiar with those. And now we can find out what dy dx is going to be. That's going to be dy du, which is of course secant square of u times du dx. That's 12x cubed. And I'm going to put the 12x cubed in front. And that'll be multiplied by the secant square of, I'll substitute that u with 3x to the 4th because I want that in terms of x. So the derivative of tangent of 3x to the 4th will be 12x cubed secant square of the quantity 3x to the 4th. So that's using version 1. Now, if I used version 2, this is what I would do here. Take the derivative of the tangent, which is of course secant square of 3x to the 4th. But then I have to get the inside derivative of that function. That 3x to the 4th, its derivative will have to be 12x cubed. And if I simplify that, I'll bring the 12x cubed in front, and that'll be multiplied by the secant square of 3x to the 4th. So you can see you can use either one of those 2 versions and get the same derivative. Okay. All right, now let's look at the chain rule for powers. If G is differentiable for all x in its domain and n is an integer, then this will be our derivative here. With respect to x of g of x, and that's to the nth power. Here we bring the power down, copy over the g of x, and that'll be raised to the 1 less power n minus 1, and then we take the inside derivative, g prime of x. Okay. So let's say we had this example. Let's say we want to use that theorem to complete this example here. And that's pretty much similar to version 2 of the chain rule that I just introduced to you. So here in example 4, we want to use the chain rule to calculate the derivative of the following function. Y is equal to the quantity 7x minus 15 raised to the 7th. So here I'm going to find out what dy dx is going to be. Or you can use y prime as this notation for the derivative. Now, using this, we would bring down the exponent of 7 in front, copy over that 7x minus 15, and that's going to be to the 1 less power, 7 minus 1. That would be 6. But we're not done yet. We have to take the derivative on the inside, which is 7x minus 15. The derivative of 7x minus 15 would be just 7. And then if we simplify this, I can multiply 7 times 7, which will be 49. So it'll be 49 times the quantity 7x minus 15 raised to the 6. I will go no further with that problem. So that would be the derivative of y. Okay. Here's another example where we're going to be using version 2 of the chain rule to calculate the derivative of this composite function. Y is equal to the quantity x squared plus 3x minus 1 raised to the 9th power. So in this case here, to find dy dx, here we bring the exponent in front. So we bring down the 9, copy over the x squared plus 3x minus 1. That would be to the 1 less power. 9 minus 1 would be 8. And then we got to get that inside derivative here. The derivative of x squared plus 3x minus 1. Well, let's take the derivative of x squared. That has to be 2x. The derivative of a plus 3x will be a plus 3. The derivative of minus 1 will be 0. Okay, if I kind of straighten this up a bit, this will be 9 times the quantity 2x plus 3 multiplied by the quantity x squared plus 3x minus 1 raised to the 8th. Okay, example 6. Say I want to use version 2 of the chain rule to calculate the derivative of the following composite function. Here I got y is equal to the square root of 7x minus 19. Now, this is somewhat similar to y equal to the square root of x. And if you recall from a previous video, if I have y equal to the square root of x, that means that its derivative is going to be 1 over 2 square root of x. All right, 1 over 2 square root of x. So if I'm going to use version 2 of the chain rule, the derivative of 7x, the derivative of the square root of 7x minus 19, using the fact that dy dx is 1 over 2 square root of x, this will be 1 over 2 square root of 7x minus 19. And then I have to multiply that by the inside derivative here. For 7x minus 19, its derivative will have to be 7x. Not 7x, just 7. Inside derivative, there would just be 7. And then if I simplify this, dy dx will be equal to 7 on top over 2 square root of 7x minus 19. But let's say you didn't know right off the top that that the square root of x was equal to, well, the derivative of the square root of x was 1 over 2 square root of x. You could write it like this. You can write that as a expression with a rational exponent, because this is the same as saying y is equal to 7x minus 19, and it is the square root. So that means in exponential form, it means 1/2. Okay, square root means in exponential form to the 1/2 power. And take the derivative from that. So dy dx would be something like this. Bring the exponent up 1/2 in front, copy over the 7x minus 19. This will be to the 1 less power, so if you do 1/2, If you do 1/2 minus 1, that'd be negative 1/2. And then your inner derivative means this. The derivative of 7x minus 19 would be 7. Now, if I simplify this a bit, the 7 goes in the numerator, that 2 goes in the denominator, and the 7x minus 1 minus 19 will go in the denominator as an expression to the positive 1/2 power. And then I can write it back as a square root. So it'll be 7 over 2 square root of 7x minus 19. Okay. Right, on the next page, let's say we want to use version 2 of the chain rule to calculate the derivative of the following composite function, y equal cosine of the quantity 17t minus 16. So if I take the derivative of that, the derivative of a cosine is going to be negative sine of that angle, 17t minus 16. And then I got to take the derivative of 17t minus 16, which is in this case going to be 17. And then let's pull that 17 in front, so it'll be negative 17 times the sine of the quantity 17t minus 16. And we are done. All right, the next example is to use the chain rule to calculate the derivative of this function. Y is equal to tangent of e to the x. Okay, so let's look at this one. We're going to do dy dx. The derivative of the tangent would be the secant square, copy over the angle, which is e to the x. Now we need to take the derivative of e to the x. Well, that's the easiest derivative to take. So the derivative of e to the x is e to the x. Okay, if you recall, the derivative of e to the x is e to the x. And now I'm going to pull this e to the x in front of secant square of the angle e to the x. And there's your answer right there for the derivative of tangent of e to the x. It'll simplify as e to the x times secant square of e to the x. All right, example 9 is using version 2 of the chain rule again to calculate the derivative of the following composite function. Y is equal to secant x plus tangent x, and that quantity is to the 8th power. And I want to find its derivative. All right, so when we use version 2, you're going to bring down the exponent in front of the parentheses. So you bring down the 8, copy over secant x plus tangent x. That will be to the 1 less power. 8 minus 1 will be 7. Now we got to take the derivative of this. Let's start with each piece. The derivative of the secant x, of secant of x, its derivative will be secant x tangent x, plus the derivative of the tangent is secant square of x. So you're probably going to need to refer back to section 3.5 to find out those derivatives of your 6 trigonometric functions here. The derivative of the secant x is going to be secant x tangent of x. The derivative of the tangent of x will be secant square of x. Now let's simplify this a bit. I'm going to bring down the 8 times the secant of x plus tangent x raised to the 7th. And notice here we can factor out secant of x. So if I factor out the secant of x here, I'll be left with the tangent of x. Plus, if I take out one of the secant of x's, I'll have only one left over, secant of x. Okay, now in the next line, I'm just going to bring this down, 8 times the quantity of secant x plus tangent x. That quantity is to the 7th power. That's going to be multiplied by the secant of x times the tangent. In fact, let me reverse this using the commutative property, just changing the order of this as secant x plus tangent x. Now notice I got secant x tangent plus tangent x raised to the 7th, and then I got secant x plus tangent x raised to the 1st power. I'm multiplying powers of the same base. That means I can add this exponent and that exponent of the common base. So 7 plus the 1 would be 8. So I have 8 times the secant of x plus the tangent of x, and that's going to be raised to the 8th power times secant x. And in this case, I will go no further than that. So that would be the derivative of our y equals secant x plus tangent x quantity raised to the 8th. All right, let's look at this example. Let's say I want to use the chain rule to calculate the derivative of this function, y equal 4x to the 6 minus 3x cubed plus 2, and that quantity is to the 22nd power. And I'm going to find this derivative. Well, let's do this. For dy dx. Here we're going to use version 2 by bringing down this exponent of 22, pull that in front, copy over the 4x plus 6 minus 3x cubed plus 2. That quantity will be to the 1 less power. 1 from 22 is 21. We're not done yet. We got to take the derivative of that inside function. That's at 4x to the 6 minus 3x cubed plus 2. The derivative of 4x to the 6 will be 24x to the 5th minus the derivative of 3x cubed. That will be 9x squared. And I'll just rearrange the terms here a bit. I'll put that 24x to the 5th minus 9x squared where the 22 is, and then 4x to the 6 minus 3x cubed plus 2 raised to the 21st power as that. So that would be the derivative of y equal the quantity 4x to the 6 minus 3x cubed plus 2 raised to the 22nd power. All right, example 11. Let's say I want to use the chain rule to calculate the derivative of the following function. Here we got y equal the quantity sine of x plus 2 cosine of x. The whole thing is raised to the 6th power. So here dy dx, let's use version 2 by bringing the 6 in front, copy over the sine of x plus 2 cosine of x. That will be to the 1 less power. 6 minus 1 will be 5. And then we got to take that inside derivative here. Let's take the derivative of each piece. The derivative of the sine of x is the cosine of x. The derivative of the cosine of x will be negative sine of x. So I'm going to have a minus in front of the 2 times the sine of x. And I'm not sure how they want that in the homework for my math lab, but I think if you leave it like this, you should be fine. They might want something like 6 times, and then they put cosine of x minus 2 sine of x in front. And then they put the sine of x plus 2 cosine of x, that quantity to the 5th behind it. All right, and it all depends upon what they want in my math lab. Now let's say we have the composition of 3 or more functions. So that's the next thing we'll look at here. We can differentiate a composition of 3 or more functions by applying the chain rule repeatedly. Okay. So with a composition of 3 or more functions, you have to apply that chain rule repeatedly. Like in this example, y is equal to the square root of 1 plus tangent square of x. Now, this is the square root of something, so that means the derivative of the square root of something will be 1 over 2 times the square root of, what's underneath that radical, 1 plus tangent square of x. And then that's going to be multiplied by what's inside the radical. The derivative of 1 will be 0, but the derivative of the tangent of x, okay, I had to think about that. The derivative of the tangent of x, you do this. Bring the 2 in front of the tangent, so it'll be 2 times the tangent to the 1 less power. So it'll be tangent to the first, or just tangent of x. But we're still not done yet. We need to take the derivative of the tangent of x, which is secant square of x. Okay, now what I could have done here is this. That tangent square of x, I could have wrote it like this. That way you can see, you bring the 2 down, copy over the tangent to the 1 less power, and then you have to take the derivative of the tangent of x, which is secant square of x. Okay. Now, if I simplify this, I would get this. Here, these 2's divide out, as you're going to see. Those 2's divide out. I'm going to be left with, in the numerator, tangent of x, secant square of x. And that's going to be all divided by the square root of 1 plus tangent square x. And I think that's as far as I'm going to go with that problem. Okay, so that would be the derivative of y equal to the square root of 1 plus tangent square of x. All right, here's the next example. Let's say we got y equal to the cosine of 19 e to the x. Okay. So if we apply that chain rule, you're going to do this. First of all, you take the derivative of the cosine, which is, of course, negative sine. So it'd be negative sine of, I copy all of this over cosine of 19 e to the x. And then I'm going to multiply that by this inside derivative of these parentheses on the outside, the cosine of 19 e to the x. Well, the derivative of the cosine, again, that's going to be negative sine times, copy this over 19 e to the x. But I'm still not done, because I got to take the derivative of 19 e to the x. Well, let's bring over the 19. That e to the x is the easiest derivative to take because the derivative of e to the x is e to the x. Okay, so now I'm going to try to clean all of this up a bit. Let's see, negative times negative will be a positive. And I'm going to pull that 19 e to the x in front. So here, cosine 19 e to the x times the sine of 19 e to the x. And that is it right there. I would go no further than that. And I left on a set of parentheses here. Oh. Right. The last thing we'll talk about is how to combine rules here. Because sometimes the chain rule is often used in combination with other types of derivative rules that we talked about earlier in previous videos. Like in this one, y is equal to the quantity 8x divided by 9x plus 8. The whole thing is to the fourth power. And I'm going to use the chain rule to find dy dx. So here's what we have in this case. Apply the chain rule, we bring the exponent in front, which is the 4, copy over what's in the parentheses, the 8x divided by 9x plus 8, raised to the 1 less power. So it'll be 4 times the quantity 8x divided by 9x plus 8, all raised to the 3rd power. But we got to take the derivative of this inside function right here. Notice we have a numerator and a denominator, so that means we need to apply the quotient rule. Okay, we need to do the quotient rule here. All right, and when we do the quotient rule, this is my high and this is my low, so this means low, which is 9x plus 8, times the derivative of the high, the derivative of 8x would just be 8, minus your high, which is your 8x, times this derivative of the low. The derivative of 9x plus 8 would be 9. Oh, that's over the denominator square. 9x plus 8 squared. Okay. Yeah, I applied the chain rule and then had to use the quotient rule. Now let's clean this up a bit. I'm going to bring down the 4 times. The 8x is going to be cubed. So I'm going to write this as 8x, and that's cubed. The 9x plus 8 is also cubed. So I'm going to write it like this, okay? Because you have a quotient raised to a power, then you can raise the numerator to that power and the denominator to that power. Now, inside this bracket, I'm going to distribute the 8 over the 9x plus 8. That will be 72x plus 64. And then minus 8x times 9 would be 72. All that's divided by, and I'm going to rewrite this as just 9x plus 8 quantity squared. I'm not going to simplify that out. Now let's simplify the bracket. What's in the bracket? 72x, and this should be minus 72x here as well. That adds to 0. So that's gone. You'll be left with 64 in the numerator. So I'm going to have 4 times 8x, and that's cubed, over 9x plus 8, quantity cubed, times 64 over 9x plus 8, quantity squared. All right, in this case here, let me simplify 8x cubed. This will be 4 times. 8x cubed would be 8 to the 3rd. That's going to give me 512. X and I cube it would be x cubed times 64. All that's divided by. Notice in my denominator. Okay, multiplying powers of the same base. I bring the base over, add the exponent. So that base is going to be 9x plus 8 raised to the 3 plus 2, which is 5. Now let's multiply the numerical terms here. 4 times 512 times 64. Four times 512 times 64. That's going to be 131,072. 131,072. Bring down the x cube. All that will be over the quantity 9x plus 8 raised to the 5th. And that will be the derivative of this function using the chain rule. All right, and finally, say I want to use the chain rule combined with other different differentiation rules to find the derivative of this function. Y is equal to the cotangent of 14x times e to the x. Now, we need to find the derivative of the cotangent. So back in section 3-5, we talked about the 6 trigonometric functions here, and one of them is finding the derivative of the cotangent of an angle. The cotangent, its derivative is going to be negative cosecant square of this. So we copy this over. But we got to take this inside derivative here. Notice we got 14x times e to the x. That means we need to apply the product rule for taking that derivative. So that inside function, we need to use the product rule. Okay. So that 14x will be the first, e to the x will be the second. So in this case, it will be first, which is 14x times the derivative of the second, the derivative of e to the x is e to the x plus the second, which is e to the x, times the derivative of 14x. That's going to be 14. And keep in mind, the derivative of e to the x is e to the x. That's the easiest derivative that anyone can take. Now let's simplify this. Bring down negative cosecant square of 14x e to the x. And let's work inside that bracket there. Here I got 14x e to the x plus 14 e to the x. And now inside that bracket, I can factor out just 14 e to the x. Because I got 14 in both of these, e to the x in both of these. So let me bring down negative cosecant square, 14x e to the x. Factor out the 14 e to the x. Well, if I factor out 14 e to the x, I'll be left with an x here. 14 e to the x divided by itself, that's a plus 1. And you'll know what I'll do here, I'll bring down the negative and bring the 14 e to the x in front. Times x plus 1, I'll bring that in front. Then copy down cosecant square of 14x e to the x. And we are done with that problem. So the derivative of cotangent 14x e to the x will end up being negative 14 e to the x times the quantity x plus 1 times the cosecant square of 14x e to the x. Okay, so that does conclude this video in section 3.7 dealing with the chain rule. Again, feel free to contact me if you have any questions about any of the problems that are presented in this video or any of the homework problems that are in our math lab for this section on the chain rule.